Okay, here we go. Lesson 1, Unit 4, Torque and Equilibrium. So, um, yeah, Unit 1, we talked about kinematics. 2 was all about forces. 3 was work, energy, and momentum. And now this section here on torque is going to take a lot of the stuff that we looked at in the dynamics section and tweak it a little bit. So in the dynamics section, we were looking at pushes and what forces were involved in pushing and pulling objects, making them move like that. Torque is torques cause rotational motion. So it's not just as simple as looking at the force and saying, okay, well, this force makes this thing spin, and so here's the torque on it. It's not much more complex than that, but it's not quite that straightforward. So here are all the things that we're going to do. So let's get started. So just like when we were dealing with dynamics and we had net forces and we were dealing with work energy, we had net work where work was based on the net force. There is a net torque concept here as well. So torque is this idea of leverage. How easy is it to spin something? It's the rotational equivalent of force, and forces are involved in this. The idea here is if a net torque acts on an object, if there is a net torque, the object's going to spin. So if the object is not spinning, there is no net torque. So you can consider what happens when you push on a door. So here's you pushing on a door, or here's the top view of that. Here's the door, there's the hinges, and you're pushing here. I don't know how many of you have tried to do this, but if you push here, it's a lot easier to open the door than if you push right near the hinge, and that's that idea of leverage. So torque here depends not just on the force that you're applying to the object, but on how far away you are from in this case it's a hinge, but in general we're going to call these things pivots. So this is distance from the pivot, r. So we've got torque dependent on both force and that distance to the pivot. Sometimes this distance from the pivot is given the letter d. We can use those interchangeably. It doesn't really matter. The reason they use r is because generally when things spin, it's a circular kind of thing, and so this you can think of as being kind of like a radius of the circle created by the spinning object. So that's why r. So torque is a vector because it has a direction. The directions are not typically what we associate with forces, but we'll get there in a second. Torque is given to us by this Greek letter tau, curly t. It's a vector, so there's going to be an arrow above it. And we can see here that it's dependent on the force and the being applied some distance from the hinge. And so the formula that we get here is that a torque is equal to a force times some distance from the pivot, and both of these are vectors as well. So we're going to multiply these two vectors and get another vector, which is interesting. For those of you who've done IB math, this is a way of multiplying vectors that you haven't seen yet. I'm going to go back up to this problem. I'm going to redraw it here, and I'm going to change it ever so slightly. So we've still got this this distance here, r. I know I've shortened the door a little bit, but we've still got this distance here, r. But what happens if I push on the door? I don't just push on the door this way, I push on it on some angle. I'm pushing that way, there's my force. What part of that force is actually, and I'll give it some angle here, we'll call it theta. What part of that force is actually responsible for causing the door to spin open? Like if we look at this here, we can look at components of the forces again. So I'm going to have this is going to be my fx and this is going to be my fy. If that's theta there, then this is also theta there. If you remember your angle relations from, you don't even remember what grade that is now. These two angles are the same. So if you look at these two components, what portion of the force is actually responsible for making that thing spin? And well, I'm hoping it's relatively obvious here that it's this Fy component here that causes the door to spin. This Fx component won't actually make the door spin. It's actually going along the door. And so, I mean, it's going to pull on the hinge a little bit. This one is the one that's actually going to cause it to swing open. And so instead of calling these things Fx and Fy, sometimes they're called F parallel and F perpendicular. We saw that already when we were looking at the inclines. And so the idea here is that for a force to apply a torque, we have to consider what portion of the force, or if the force is at all perpendicular to the radius or the object, the distance from the pivot that we're spinning this thing. If this was the only force I had on here, the door wouldn't spin. I'd rip it off its hinges. And this guy here, this one's perfectly perpendicular, so it's all the force is going to go into making that door spin. And so we're going to actually tweak our equation here for torque a little bit here. It's not just torque equals the force times the distance from the pivot, or I'll say Fr. But what we're most concerned about here is with the force being perpendicular to that distance. If you go off into university, what you're going to see here and study some physics, the actually we can look at it here. This idea of the perpendicular distance, or it's not the perpendicular distance, this perpendicular component of the force here is actually F sine theta. And so what we can do is we can go in here and we can rejig our formula a little bit here, where we can say my torque is equal to my force perpendicular times my radius, or the distance from the pivot. We can generalize this, so it's going to be my force times the distance from the pivot sine theta, where theta is the angle between F and R, which is kind of cool. And this will generalize in a bunch of really interesting ways. Like I was going to say before, if you go off into physics in university, what you're going to be introduced to is this idea of what's called a cross product. So in IB math, you did a dot product where you multiplied two vectors together a particular way. There's another way to multiply two vectors together, so we call it the cross product. So it's F cross R, and actually in general, it's given to us by this Fr sine theta. So we can make that argument here without introducing the complex mathematics, but this will come. So this is the expression that we're going to use right here. So if we look at some things here, the units for torque, it's a force times a distance, so those are going to be Newton meters. The directions of torque, if we're considering things spinning, the conventional ways that we talk about directions for spin are either clockwise or counterclockwise. If you don't know how to tell time, that's going to be very difficult. Generally speaking, clockwise goes this way, and counterclockwise goes this way, basically the opposite direction that a clock goes. We generally call clockwise positive and counterclockwise negative as far as the spinning goes. If the force acts directly at the pivot point, that would mean that the distance between the pivot and the force acting is 0, which means there would be no torque. 0. Which, if you look here, if you try to open the door from the hinges, nothing's going to happen. If there are several torques acting on an object, the net torque net, is equal to torque 1 plus torque 2 plus ... plus torque. I'll call that torque n, however many torques we have there. It's the sum of all of them. Just like when we were dealing with forces, we've got the sum of all the torques there. So let's look at an example, the classic example every one of you should be familiar with. is this thing here a seesaw or a teeter-totter. We all hurt ourselves on these things. I hope you had an opportunity to hurt yourself on one of these things as a kid. You didn't really live if you didn't. So we've got a seesaw, a 10 kilogram beam is pivoted in the middle. And so the pivot, we're told the pivot's there. One of the things I like to do is actually draw in, make it really explicit. This is where the pivot is. And there's actually going to be questions that we're going to do where you're going to see it doesn't actually matter where we put the pivot. And so for you to draw it in explicitly is actually really quite important. You can choose where to put the pivot and it'll change how the math works, but the end result will still be the same. So you can choose your pivot point to make the math turn out the easiest. So we want to draw all the forces that act on the 10 kilogram beam. And so if we think about what's going on here, we have a force downwards from this person. We've got Fg of that person acting down. We've got the 10 kilograms times 9.8 is going to give us a very light child. 98 Newton force. We have an even lighter child. Fg here is 5 times 9.8, so that's going to give us a 49 Newton force. Well, and what other forces are acting? There's got to be some more forces that act on this thing. We can see here that there's actually a bar here in the middle. If you've used a teeter-totter before, you'll know that there's a bar that goes right through the middle of the thing, so this thing can be where it pivots. This bar is actually responsible for holding the whole thing up. It doesn't slam into the ground when these people sit on it. So there has to be some normal force up there. And we know that the weight of the beam itself is 10 kilograms, and so where do we put the weight? We put the mass of the beam gets placed at what's called the center of mass. I think we've discussed this before. So this guy here gets placed at the center of mass, and interestingly enough, for a uniform object, which this bar is, the center of mass is at the center. So we're going to have Fg for the beam acting down there as well, and that's also going to be 98 newtons. So now we can actually look and see what the normal force here is. There are 3 forces acting down, there's 1 force acting up, and the beam itself isn't getting launched into the sky or driven into the ground, and so the normal force must be the sum of the upward force must be the sum of these 3 downward forces. So 98 plus 98 plus 49, which gives us a normal force of 245 newtons. So those are all the forces that are acting on that beam, and now we have to say we're going to use these forces to figure out what the torque is. So which of these forces are actually producing a torque? Well, it's not these 2 that are acting on the pivot. I mean, if you see a teeter-totter or a seesaw just kind of sitting there by itself, it's not going to be spinning wildly on its own. To make the thing move, you have to put people on it. And so you're going to have a torque that's going to make this thing, the teeter-totter, swing this way, and you're going to have a torque created by this force here that's going to make it swing that way. And so we want to figure out what these 2 torques actually do, and what we're going to do, and what we also have to do. Back when we were looking at dynamics, we had to pick a direction for positive. We actually have to pick a direction for positive spin here as well, a positive torque here as well. So it ultimately doesn't matter which way you choose. Generally speaking, we would say, okay, this is clockwise, so I'm going to call that thing positive. So let's go with that. So this person's creating a torque. Torque equals F perpendicular times the distance to the pivot. So my perpendicular force is 98 newtons. The distance to the pivot here is 2 meters. So the torque here is 196 units or Newton meters, and the direction here is counterclockwise. So CCW. You got to put all those pieces there because torque is a vector. And this guy here, it's kind of dealt with here already, actually. But I was going to say, because it's going this way, this should theoretically be negative, but we wouldn't have the negative and the counterclockwise. Just having the counterclockwise there is good enough. So this guy here F perpendicular R. That's going to be 49, and then the distance from the pivot, in this case, to the force is shorter. It's 1.2 meters now instead, which is going to give us a torque of 58.8 Newton meters. And we can see which way this thing's going. We can act it out, too. This thing's going clockwise. Oops, sorry. And so now when we add these things together, we want the net torque. We have to add together a counterclockwise and a clockwise torque. So we've already said that clockwise was going to be positive. So when I add these things together, I have to put my explicit negative sign in there. So I'm going to get negative 196 plus 58.8, and we're going to get a net torque of negative 137.2 Newton meters, which tells us that the torque, the net torque on this thing, is 137.2 Newton meters counterclockwise, i.e. the teeter-totter is going to do this and then presumably stop when it hits the ground. Excuse me. So if the net torque is counterclockwise, the object is going to spin counterclockwise. If the net torque is clockwise, there will be some sort of spin clockwise. I don't know what happened to that P there. Anyway, spin clockwise. And if the object is not spinning, then there is no net torque. So let's look at a couple more examples here. If the pivot in this is not located at the center of the object, then the weight of the object is going to cause it to spin. So the teeter-totter itself, though we didn't consider the mass of the teeter-totter causing spin, because that was right at the pivot and the center of mass were located at the same spot. But something like this, like if I'm holding a meter stick and I hold it here, then I mean you've all held heavy objects. The object wants to spin kind of out of your hands, and so this is where the concept of center of mass comes from, because we can't consider all of the little forces acting on every minuscule piece of the object. We say, okay, well, if I condense all of those tiny forces into the center of mass of the object, I can consider one force acting at one position, because otherwise it gets far too hard. So we can take gravity to act on the average at a single point, and the average position is what we call the center of mass. And for uniform objects, i.e. the object is the same throughout, that is at the middle. So here we are. Yet the pivot is over here this time, where you're holding the meter stick. If this is, let's say that this is a, I don't know, it's not obviously this can't be a meter stick. Let's say this is a 2 meter stick. Those don't exist, but that's okay. It's going to be 1 meter. It's going to act in the center of the stick, and so we're going to have FG acting straight down there. So the classic example for this is something like this: a crane. So we've got, if this is a crane, just draw that in there. There's going to be, the cranes generally have a sliding cable that goes down to the ground, picks something up. But this, let's assume this crane, and the counterweight here, because if this counterweight didn't exist in this object and the crane went to pick something heavy up, then the whole thing would just go slamming into the ground. So generally speaking, there's a counterweight at the back of these things. And so we want to find the net torque on, so we're told that this, obviously this can't be an entire crane. This is an 8 kilogram, 5 meter long uniform beam with a 20 Newton weight attached to the left end here. So it's a tiny crane, it's a toy crane. So the first thing we want to do is we want to write down or add to our diagram all the forces that are acting on this object. So there's a force of gravity down here. We're told that the weight of this thing is 20 newtons, so that is the the force of gravity. We are told that this is 5 meters long. The distance from here to here is 1 meter. And we're told that the beam on top here is uniform. So there's going to be a force downwards in the middle for the mass of the beam. So that Fg is going to be, we know that this thing has a mass of 8 kilos. So it's going to be 8 times 9.8. It's going to have a weight of 78.4 newtons, or force of gravity acting downwards of 78.4 newtons. And so then the question becomes, well, what is this distance here? This theoretically should be at the center. I know my drawing's kind of off, but if this is acting at the middle, a 5 meter beam from the end to here is going to be 2.5 meters. If this is 1 meter, then this here is going to be 1.5 meters from the pivot to the center of mass. This is not all. There is one more force acting on this thing. We're assuming that this thing is standing stationary. The beam itself is not being launched into the sky or driven down into the ground. So again, you have to consider the normal force here, the force acting upwards from wherever the pivot is. In this case, the pivot, I've added that upward beam there. So my Fn is going to be the sum of all my downward forces, so the 20 newtons and the 78.4 newtons is going to give us an Fn of 98.4 newtons. I'm going to add in here my direction for positive. Generally, we assume that clockwise is positive, so if I go that way, what's happening here? To find the net torque, we have to find the sum of all the individual little torques. And so now we've got all of our forces labeled, so we can go ahead and do that. This force here, if the pivot's here, and this is the only force acting, this thing would go like this. And so this is going to create a torque that goes this way. This guy, likewise, if this is not here, this torque, or this force, is going to create a torque that makes this thing do this. And so this thing's going to spin down that way. And so these are the directions for the two torques here. So my torque is my force perpendicular acting some distance from the pivot. So in this case, that's going to be 20 newtons times 1. So the torque here is 20 newton meters counterclockwise. This guy, torque equals F perpendicular R, and so that's going to be 78.4 newton, or yeah, 78.4 times 1.5. That torque is going to be 117.6 newton meters clockwise. And so now if I want to find my net torque, I just got to sum these guys up. So my net torque is equal to, now if I sum these up, zoom this up a little bit. If I sum these up, I can't use clockwise and counterclockwise. I have to bring in this idea of positive and negative. We already said that clockwise is positive, so I'm going to get 117.6 minus 20. So there is a net torque on this thing of 97.6 newton meters, and it's positive. So we know the direction on this thing is clockwise. Which means that if we set this up and let it go, this thing's actually going to start crashing down into the ground, and this thing's going to get lifted up. It's going to rotate. It's not always going to be this easy. Let's look at, I think this is the last example we're going to do. Yeah, we're not going to look at, the last couple are kind of gross, and so we're just going to look at this guy, these guys here. We've already kind of said this already in the door drawing that we looked at. If the force is not perpendicular to the object, then we need to once again consider components. In the diagram below, we can see that the component of force perpendicular to the object is the one that makes the object spin. So I've got my door here again, I've got the hinges, I've got a force acting out this way. The parallel component is just going to pull on the pivot. It's this perpendicular one that's going to pull this thing down here. And so we've already written this expression down once, but we're going to write it down again. F perpendicular R is going to equal F R sine theta. Where that angle there gives us this component there. That component there is the perpendicular component of the force. The reason it's drawn like this is so that we remember that the force actually acts where this thing is mounted. But this is the triangle that we use to solve it. And so that's going to open up questions like this. We want to find the net torque on this beam shown below. It's kind of like inclines. Now we got angles and stuff coming in here. You have to make sure you keep track of all the angles that you've got. I'm going to zoom this thing in here so it's easier to see as I'm drawing stuff on here. Basically what this is we've got a beam lying on the ground that we're raising with a rope. The beam has a mass of 5 kilos and a length of 8 meters, and there's a 25 Newton tension force in the rope. So we're going to add all of these things to our diagram here. So we want to add all of the forces first. So I'm just going to draw in my tension first. Tension from the rope. How do I want to put this in here? My tension equals 25 newtons. That's one force acting on this object. My next force, you always have to consider gravity acting on the object itself. And so I've got, we're told that the mass of the beam is 5 kilograms, so the force of gravity is going to be 5 times 9.8. It's going to be 49 newtons. And this object is resting on the ground, so at this point right here, there's going to be a normal force straight up. And in this case, we don't know what that's going to be yet. The question is, does that even matter? So there's only 3 forces acting. Those are them. Now the question we're looking at, we want to find the net torque on the beam shown below. So what? Now we consider what forces are actually contributing to that torque. This is where the object is pivoting. I'm just going to explicitly draw that pivot in there. We've already said that forces that act on or act at the pivot aren't going to contribute to the torque. And so this thing, in this particular question, this guy here causes no torque. So in this particular question, we can actually ignore him, which is going to be great. So let's take a look at what we've got going on here. We've already said that torque is equal to the F perpendicular, or the perpendicular component of the force times the distance acting from the pivot. And so I want to draw some distances in here. My pivot's here at the end of the beam. This distance here, this is gravity. And so we're told that the beam is 8 meters long. So this distance here is going to have to be 4 meters. This, we're told, is half a meter. So the distance, I'm going to draw in another color just so we can see this. There's going to be a lot going on in this picture. This distance here. So what is the distance from the pivot? Is 7.5 meters. Now, if we look here, we're going to do some drawings. Neither of these forces are acting perpendicular to our beam, and so we're going to add in those perpendicular components just so we can see what's actually going on here. This right here is FG perpendicular, and this guy right here is our perpendicular tension. Now, we've already said that it's FR sine theta, but some of you are going to look at this thing and say, well, it'd be so much easier just to use this angle in here. In this case, this would be my hypotenuse, this would be my perpendicular component, so I would just use the cosine then of 50. One of the things to recognize, though, is that cos of an angle is equal to sine of 90 minus an angle. So if this is 40, this is going to be 50. So we use cos of 50, but cos of 50 is just the same as 90. Sine of 90 minus 50, which is sine of, in this case, it would be the sine of 40. So, for example, the cos of 50 equals the sine of 40. And just the way that torque is defined, we want to use sine here, just to continue to be consistent. So this perpendicular torque is going to be 25 sine 40, acting from that pivot. And this perpendicular component of gravity, well, is going to be what? If this angle here is 35 and this is straight down, then this angle right here is going to be 55 degrees. And again, we always want to consider the force, the angle between the force and that distance. And this is the smaller of those two angles. So this guy here is my force. This guy here is the distance. And so that angle in there is the one that we want to use. So we're going to take the sine of that angle. So it's going to be my force, 49 newtons, times the sine of the angle between them. So in this case, it's going to be sine 55. So now when we go through and we want to find these two torques, we're going to have the torque from the tension in the rope is going to equal my force, 25, times the distance, 7.5, times the sine of the angle between them. So we can see here how we've dealt with the, I'll zoom this out again a little bit here. We've dealt with the perpendicular component already. We've got the 25 sine 40 times the distance from the pivot. So the torque from this tension is going to be 120.52 Newton meters. This rope here is going to pull this thing so it spins this way. That is counterclockwise. Oh, one of the things we didn't do is define a direction. Again, generally we assume that clockwise is positive. So now let's look at the torque from gravity. Torque from the gravity is going to be Fr sine theta. So the force of gravity is 49. The distance from the pivot to there is 4 meters. And the sine of the angle between them is 55 sine 55. So we can already see here that 49 sine 55 gets taken into account if we use this formula properly. And then we've got R, the distance from the pivot to where the force is acting. So then the torque from gravity here is going to be 160.55 Newton meters. And now this guy is acting clockwise. So my net torque, this one clockwise is defined to be positive. So it's going to be 160.55 minus my counterclockwise torque. It's going to give us a net torque of 40.03 Newton meters clockwise. So what does that actually mean is happening? This beam is being lowered slowly to the ground is what's actually happening there. So this is going to be the last example. I'll talk briefly about some of the other stuff on the next couple pages, but ultimately they're going to be concepts that we don't necessarily need to look at. This example is pretty key to where we're going forward here, or we are going forward here. So there's other techniques for determining this as well. Don't worry about this page. Don't worry about the stuff going on here. These are examples of much more difficult torque problems. Instead of using the perpendicular component of the force, these things are arguing that instead of looking at the perpendicular force component, you can actually look at the perpendicular distance component. That is really quite useful when you're looking at much harder torque problems like this one, the sit-up problem, where you've got your abs pulling down and you've got gravity pulling you down from your center of mass in your torso. Again, you're not uniform, so the center of mass is actually higher up in your chest. So those are the kinds of, that particular concept we can use to look at problems like this. I'm not going to go through that with you, which means I'm not going to assign it to you, so don't worry about those kinds of things. Because ultimately, this particular kind of problem would be fairly difficult. If this is where your abs are, obviously this is closer to your neck than your abs are actually attached, but if your abdominal muscles are attached up here, this would be the distance from the pivot that you'd want to look at here, and then we'd have to figure out what that angle is in there, and that would be gross and kind of hard to do. The argument here is that instead, if we use the force acting the way it is and the perpendicular distance here, the problem becomes a lot more easy. So we could have F perpendicular R is equal to FR sine theta, or the argument here is that we could have FR perpendicular, which is just going to be the same FR sine theta. That's the argument for doing this. If you want to see this, I can show you an example. Fire me an email if you want to see this particular example, but otherwise I'm just going to pass on it. So the questions that I'd like you to take a look at for this section here on torque are the following. I would like you to do 1 to 3, 5, and 7. Comments, questions, concerns, fire me an email, and good luck.